Dear ladies and gentlemen, my name is Martin Mojto. I am a PhD student at Slovak University of Technology in Bratislava, and today I would like to show you the results from our research focused on the design of multimodal linear inferential sensors with SVM-based switching logic. So the inferential sensors are frequently used in the industry, especially in the case of the distillation columns, where usually many online sensors are available, and these sensors communicate with the advanced process controller, which uses the information from these sensors to provide adequate or efficient action to maintain the process in the desired operation. Sometimes there is one or more key process variables which have potential to further improve the performance of the advanced process controller. This kind of variable is, for example, the concentration of the bottom product. The problem with these key process variables is expensive or inaccurate or infrequent measurements with the ordinary sensing devices. And this is the motivation for the design of inferential sensors, which represents the cheaper alternative. And basically it uses the data from the selected online sensors and from the lab analysis. The data is time aligned and sent to the offline phase of the inferential sensor where the design is carried out. Subsequently, it's possible to use the measurements from the selected online sensor to generate the prediction of the desired variable in the real time. This predicted variable can be subsequently used as an additional input to the advanced process controller. In this research, we would like to compare the performance of the single and multimodal inferential sensors. But before we are going to talk about the details of these approaches, let's have a look at the performance or the behavior of the key process variables. It can be represented by the pressure compensated temperature model illustrated in this figure. And according to our experience, this model have potential to quite precisely explain the key process variables in the distillation columns. This is the reason why we use this model for the design of inferential sensors in our research. But in the following sections, we are going to use even simpler 2D example to introduce the methodology in a simpler and more transparent way. So let's have a look at the design of the multimodal inferential sensors. So two classes of measurements are considered, and the first step of the multimodal inferential sensor represents the a priori labeling of the training dataset. This can be done by the k-means clustering, and the results is presented in the figure. Subsequently, the classification can be performed according to the obtained labels from the first step, and the separation hyperplane can be designed. In our case, we consider the support vector machine, which provides us the linear separation hyperplane. Subsequently, the classified datasets can be used to design the individual sensors, and all these three steps together forms the state-of-the-art approach for the multimodal inferential sensor design. Even though that this approach seems to be quite sophisticated, there is still space for the improvement. In this case, we would like to focus on the two challenges. The first one is that the design models of the inferential sensors are not necessarily continuous, which can be seen in this picture. The second challenge is that there is unknown impact of the a priori labeling on the multimodal inferential sensor accuracy. So, for example, in this picture we can see one way of the data clustering but there are more ways how to perform the clustering, and it's a question which one is the most efficient with respect to the overall performance of the inferential sensors. So in order to provide the solutions to these challenges, we need to make some changes in the structure of the state-of-the-art approach. So basically we combine the second and third step together, and we obtain the following optimization problem, which involves the select variables from the support vector machine methodology, sum of squared errors criteria from the sensor training, and also here we consider the binary variables, which represents the assignment of the measurements to the considered classes. So according to this optimization problem, it's possible to deal with the first challenge, which is about the discontinuity of the design models within the multimodal inferential sensors. Here we adopt the continuity constraints, which ensure that the design separation hyperplane should be located right on the cross sections between two models. So we can simply implement these constraints into our optimization problem, and as we can see, the design models are now continuous, which can be seen here. So this leads us to the first proposed approach for the multimodal inferential sensor design with continuous labeling. But we can go further and provide the solution to the second challenge, which is about the unknown impact of the a priori labeling on the multimodal inferential sensor accuracy. Here we can effectively use the binary variables, which defines the assignment of the data into the different classes. So basically we start to optimize this vector of the binary variables, and this allows our optimization problem to consider the a priori labeling during the design of the multimodal inferential sensor by simultaneously solving all three tasks of the original state-of-the-art approach. This leads us to the second proposed approach for the multimodal inferential sensor design with optimized data labeling. In order to provide the computational load analysis of this proposed approach, we use two different solvers. The first one is the Baron and the second one is the Gurobi. In the case of Baron, we consider also the heuristic termination. So now we can go and analyze the performance of the proposed methods on the desired case study. So therefore we move from this simple example to the pressure compensated model, and here we study the different scenarios. The first scenario is that we have three visible classes of measurements, and we can also see that the measurements are randomly distributed to the training and testing data sets. This table represents the results from the design of inferential sensor according to this scenario. And what we can see here is that the approaches without the optimization of the binary variables achieve significantly lower computational load compared to the other approaches. We can also see that the multimodal inferential sensor with optimized data labeling designed by Gurobi is more precise compared to the other approaches. And we can also see that the optimal balance between the model accuracy, computational time, and model continuity provides us the multimodal inferential sensor with continuous switching. Subsequently, we can visualize the design of the multimodal inferential sensor. For this purpose, we use the training dataset, and the considered methods is the most accurate one, which is the multimodal inferential sensor with optimized data labeling provided by Gurobi. So this approach simultaneously classified the data into the following three classes and designed the models of the inferential sensor illustrated here. So as we can see that the designed models are have continuous switching, and we can also see that this approach is trying to explain mainly the nonlinear section of the pressure compensated temperature model. This leads us to the second scenario where the uniformly distributed dataset is considered. Due to the random character of this scenario, we consider 100 different uniformly distributed datasets, and the following results represents the statistical evaluation from these 100 different datasets. So here we can see the same results as before. So the approaches without the optimization of the binary variables achieve significantly lower computational load. And we can also see that the other or the rest of the approaches is also affected in a way that the results are more have higher variability. But we can still see that the multimodal inferential sensor designed by Gurobi achieves the highest accuracy compared to the other approaches. And also the multimodal inferential sensor with continuous labeling represents the best balance between the model accuracy, complexity, and the continuity of the design models. Subsequently, we can illustrate the design of the inferential sensors as before. So for this purpose, we also use only the training dataset, and we consider the most accurate approach. And this approach is simultaneously clustering the datasets and designing the models of the inferential sensors, which are illustrated here. And as we can see, the models have continuous switching, and also they are trying to explain the ground truth model. Where this leads us to the conclusions where we would like to emphasize that the most accurate approach is the multimodal inferential sensor designed by Gurobi. But we would like to also emphasize that the multimodal inferential sensor with continuous labeling provides the optimal balance between the accuracy, computational load, and the model continuity. And finally, the optimization of the binary variables causes significant computational load and variance in the results. In the future, we would like to increase the analysis of the multimodal inferential sensor about more advanced approaches, allowing for allowing for the consideration of different model structures. And we also would like to consider various approaches from the data treatment to enhance the quality of the data. So this is all from my side. Thank you very much for your attention, and if you have any questions, please don't hesitate to contact me.